Okay, let's take a look at solutions. We mentioned solutions before in the very first unit. A solution is a homogeneous mixture. It's a key word there. And homogeneous means that once this type of mixture is formed, the components are not distinguishable. They look the same. All right, so one word for homogeneous mixture is solution. And the most common solutions in this course are liquid solutions. So let's go over some of the properties, 3 properties that all liquid solutions have in common. And that is they won't filter. For example, when you dissolve salt in water, the salt that's dissolved cannot be filtered out because the particles are just too small. They won't settle. The salt that's dissolved won't settle to the bottom of the test tube. And all liquid solutions won't block light. In other words, they're transparent. Just think of a container of salt water. You should be able to see through it. If it's cloudy, then whatever's there is not dissolved. All right, and that would be a heterogeneous mixture. So once again, the reason for these 3 properties of solutions is the fact that the particles are too small. Now let's go over the equation for dissolving. Dissolving in this case, sodium chloride in water. And the same format would apply for anything that dissolves in water, and that is you begin with the solute on the left side, the sodium chloride as a solid. In this case, if we're dissolving solid solutes, you put the S here, and then the water over the arrow is the solvent, since we're talking about aqueous solutions in this case. And in the case of NaCl, since the water splits the compound, it separates the ions from each other, we'll end up with Na plus AQ and Cl minus AQ. And that would be hydrated ions, which means that the sodium and chloride ions have been separated from each other through the process of dissolving, and they're kept separated because the water molecules surround each of the ions. Why that occurs is because the water molecule, if you recall, is a polar molecule. So it has a negative and a positive pole. And there will be an attraction for the sodium ions between the sodium ions and the negative pole of the water molecule, which is the oxygen atom. And these attractions, of course, as mentioned in the bonding unit, are called molecule-ion attractions. The intermolecular attractions in this case are called molecule-ion attractions. So there's an attraction between this molecule, this polar molecule, and that positive ion. Notice how the oxygens face the sodium, and in the opposite side you would have the hydrogens facing the chloride ions, because the hydrogen atoms are on the positive side of a water molecule. So let's draw that here. Now for most solids, since the energy released when attractions form is less than the energy absorbed when bonds break, the dissolving process overall is an endothermic process. And in other words, it has a cooling effect. So let me elaborate on that. And that's what these arrows here represent. In order to separate these ions from each other, energy has to be absorbed. E, absorbed. And when the water molecule attaches itself to these ions, either the positive or the negative ion, energy is released. And what I'm saying is, in the case of most solids, the energy absorbed is greater than the energy released. So that energy has to come from somewhere. And in that case, it comes from the thermal energy of the water itself. So the dissolving process has a cooling effect. What that means is, simply put, if you have a container of water and sodium chloride, for example, is being dissolved in it, the temperature of the water will tend to decrease. And more, depending on the salt that's being dissolved. So let's see if we could draw that here on the side. So again, if this represents the container of water, you have some sodium chloride here. We'll just take that as a cube of NaCl, which represents millions and millions of positive and negative ions. As this gets dissolved, what I'm saying is, if you had a thermometer here, the temperature would decrease. That is, the temperature of the water would decrease. Because overall, there is more energy absorbed in the dissolving process than released. So, a cooling effect is what I would remember. In fact, you could start with that. Most solids, it's a cooling effect. Now, in the case of NaCl, we have a salt that is common and clearly soluble in water, but not all salts are soluble in water, as you'll see in a second, or as soluble in water. When it comes to predicting the solubility of different substances in water, or different substances in each other, the guiding rule is like dissolves like. And that's the reason why oil doesn't dissolve in water, because oil is nonpolar and water is polar. So in this case, the intermolecular attractions holding the oil molecules to each other are very different from the intermolecular attractions that hold the water molecules from each other. And so, since they're different, they won't dissolve in each other. The energies just won't match. All right, so like dissolves like is really the guiding rule here. And that's why I always say LDL, not LOL. Just a quick way to remember that. So what we're saying is, the reason why alcohol dissolves in water is because alcohols are polar and water is polar. So like dissolves like, polar with polar. On the other hand, oil does dissolve in something. It would have to dissolve in benzene, as an example, because benzene, like oil, is nonpolar. So you have nonpolar dissolving with nonpolar. And of course, the case of salts in water, as we just mentioned a second ago, is a case of an ionic compound, because salts are ionic compounds, dissolving in water because of the molecular ion attractions, or the molecule ion attractions that we just mentioned. All right, but sodium chloride, as I said a second ago, it happens to be a soluble salt in water. And the table that you have, table F, you could use that table to guide you in predicting the solubility of different salts in water. Remember, salts are ionic compounds, so there's going to be a positive and a negative side to all of these compounds. Now, technically, all salts are soluble to some degree in water, but in table F, they divide it into two camps, the salts that are soluble and not soluble. All right, so if you're asked to predict the solubility of a salt, and these are all salts or ionic compounds in water, what you do is start with the second half of the formula. All right, so for example, in the case of BaSO4, if you recognize the sulfate ion, that would be the second half. And what you do is, you go to table F, and you look up for the SO4. Look up the SO4. The SO4, under the sulfates column, we're told here that they form soluble compounds, but they do have exceptions. And the exceptions are when the sulfates are combined with Ag+, Ca2+, Sr2+, Ba2+, and Pb2+. So since the Ba2+, which is what this barium ion is right here, is an exception to what is soluble, then this thing would be not soluble. I'll say it again. Because Ba is an exception to a sulfate that ordinarily would be soluble, you can think of this exception as not soluble. Again, let's look at the second half of this compound here. And we have CO3. Now, even if you know the name of this polyatomic ion, all you have to do is find it in table F. and you'll find the CO3 negative 2 ion is for carbonates. And in table F, the carbonates are underneath the insoluble compounds column. So carbonates in general are insoluble. Now the question is the Na an exception to that? And if you look again under the carbonate column, you'll see that the exceptions are when combined with group 1 ions or ammonium. And sodium clearly is in group 1. So this is a group 1 exception to something that is normally or ordinarily insoluble. So it's not insoluble, which makes it soluble. All right, why don't you try doing the next two and see if you could figure it out using table F. And you'll see that the CaCl2, again looking at the second half, you'll find the Cl minus ion, the chloride ion under the halides on the left side of the table. And we're told that halides are ordinarily soluble with 3 exceptions, and clearly the Ca is not one of those exceptions, so that makes this soluble. And then let's look up the aluminum hydroxide here, again looking up the OH, and you'll find it under the insoluble column, and most hydroxides are insoluble. And now the question is the aluminum an exception to that? And we're told that group 1, calcium, barium, strontium, or ammonium are exceptions, so the aluminum is not an exception, and that makes this compound insoluble. So the key thing to remember in table F, first of all, is that there are 2 columns. There are the soluble compounds with their exceptions, and then there's the insoluble compounds with their exceptions. And just think of the exception as a not, a reverse of what you have there. Okay, now that covers table F, and even for that matter touches on table E with the polyatomics, just to remind you of them. Now let's take a look at table G, which is the solubility curves. But first of all, I want to remind you that when it comes to solubility, the factors that affect solubility, I want to remind you that solubility is a measure of how much gets dissolved, the grams of solute per grams of solvent. So solubility is not just whether or not it gets dissolved, but how much gets dissolved. And you could divide solutes into 2 categories here. Those that are affected by temperature and those that are affected by pressure. All right, and when it comes to solids and gases, if you increase the temperature of the solvent, you'll increase the S, the solubility of the solid, but you'll decrease the solubility of the gas. And we're talking about solubility in this case, if you look at table G, solubility in water. All right. And then when it comes to pressure, pressure has no effect on the solubility of solids, but an increase in pressure will increase the solubility of a gas. All right, so if you look at table G, which I have a diagram below of that, you'll see that there's 2 curves here. There are curves that are going up as temperature increases, and along the x-axis here would be temperature, and this would be your solubility along the y-axis. And note, it is solute per 100 grams of water, and this is a curve of these different compounds showing you that as temperature changes, how their solubilities change. So there are 2 categories. There are those that are going up in solubility with an increase in temperature, and those solids that are going down in solubility. And simply put, you could divide them then into the solids are those that are increasing in solubility, and the gases are the ones that are decreasing. As we just said a minute ago, how an increase in temperature makes solids more soluble and gases less soluble in water. Now, if you want to remember that a little bit better, you can apply these two factors to the solubility of gases in the case of seltzer. I have a diagram of that in your notes, so let's take a look at that. Take a bottle of seltzer, which is carbonated water, and carbonated water is carbon dioxide gas, which is now your solute being dissolved in water, giving you CO2 aqueous. All right, so seltzer is CO2 aqueous. And when you start out with a bottle of seltzer, which is capped, you should see no bubbles. All right, the reason for that is because the CO2 is being kept under higher pressure in solution. Now, if you see bubbles, remember, bubbles you see is gas, in this case CO2 gas, that's not dissolved. So bubbles are gas that is not dissolved. So the first thing we do is we uncap the bottle of seltzer and we notice bubbles. So what's happening here is when you uncap it, you decrease the pressure, and as a result, you decrease the solubility of the CO2. And then what you could do is you could heat the bottle of seltzer, or in other words, increase the temperature of the solution. And when you increase the temperature of a gas, more bubbles appear, of a gas dissolved in water in this case, more bubbles will appear, and again, that indicates that it's less soluble, because the bubbles you see is gas that's not dissolved. All right, so when someone manufactures seltzer to make seltzer, what you want is just the reverse of these two factors. So to make seltzer, you want not a low pressure, but a high pressure. And the opposite of this, a low temperature. And what's true for CO2, of course, applies to all other gases. And then, looking at the solubility curves a little bit closer, once again, to remind you, solubility is a measure of how much gets dissolved. You could look up the solubility of any solute here, but the most common, of course, is NaCl, which is table salt. And if you look up the solubility of NaCl at 20 degrees Celsius in 100 grams of water, you'll find that the maximum, in this case, is 38 grams per 100 grams of water. And once you've reached that maximum, then you could say that all of these solutions are saturated. That means they've hit their limit. And whether you have 100 grams of water or 250, if you maintain the same ratio, they'll all be saturated. So just keep the ratio. And once again, to remind you, there's basically three types of solutions then with respect to solubility. You could either have a saturated solution, which would be for any point along the curve at a specific temperature. You could have an unsaturated solution if you have less than what the curve tells you is the maximum. Or you could have a supersaturated solution, which occurs rarely, and you'd have to be told that, where you could exceed what the curve says is the saturation point. All right, so a saturated solution is a solution that has reached its limit. The reason why the solution reaches a limit is because a saturated solution is at equilibrium. And what that means is that if you look at that solid that's at the bottom of the beaker, although it appears that it's not dissolving at all, that's not true. What's actually happening is, for every little amount of solute that dissolves, an equal amount comes out of solution, and that's why you see no change. So a saturated solution, again, is a solution at equilibrium because the rate of dissolving is equal to the rate of crystallizing. Remember, rate is how fast, not how much. Now we'll do some problems with solubility curves in a minute, but once again, this unsaturated versus saturated versus supersaturated is a little confusing. So let's go with respect to NaCl. Let me give you some examples. So if 38 grams is saturated, what I'm saying is at that temperature of 20 degrees Celsius, then if you had less than that, if you had 37 grams per 100 grams of water, that would be an unsaturated solution. And if somehow you were able to exceed that amount, let's say you had 39 grams per 100 grams of water, then that would be a supersaturated solution. Now, why a solution gets supersaturated, that's another matter. But you still would have to be told that, because there's no way of you guessing whether one solute or another will exceed what the curve says is the maximum. So we'll do some problems with solubility curves in a couple of minutes. But what I'd like to do now is move on to the next page on solutions. The solutions is a very brief unit, and you're going to need your calculator for the next page, because we're going to do some problems in solving for concentrations. So I'll meet you there in a second, unless you want to take a break.